Good afternoon, everyone. Aidan Murphy, sir, is currently a postdoctoral research fellow in the Complex Software Lab at University College Dublin, researching software testing and mutation analysis. He obtained his PhD in Explainable AI, XAI, in the BDS lab at the University of Limerick and completed his undergraduate degree in theoretical physics from Trinity College, Dublin. He also has an HD in statistics from University College, Dublin. His research interests are grammatical evolution, transfer learning, fuzzy logic, and XAI. Adam Murphy, sir, is going to give us a brief idea on the title and an introduction to explainable AI. Welcome, sir, and I request you to please take charge of the session. Hello.
Thanks, Ad.
Yes.
So thanks for that introduction. Good afternoon, everybody. And everyone can see my screen. That's okay, yeah?
Yes, sir.
Perfect. So I was hoping that people could just jump in if they had any questions. So feel free. So I know people will be in a hall, so it might be more difficult in an audience. So maybe in that case, wait to the end. But please just feel free if I'm maybe not explaining anything or you want me to go into detail as we go. And I've been told I can speak a little fast. So I've made this presentation a little bit shorter than usual. So maybe force me to go a bit slower. And again, if anyone wants to talk about anything in the end, we should hopefully have lots of time. But yeah, so as I was saying, this presentation will be about explainable artificial intelligence, which I guess for maybe the last 5 or 6 years has been a really popular topic both inside of academia and outside. Especially Google has spent an awful lot of money trying to like investing in this area, investing in like technology and people. Because as we kind of showed, this isn't just about engineering or somehow using statistics to gain insight into anything. This really has become like a really multi-dimensional, multidisciplinary, interdisciplinary area where you have engineers on one side, you have maybe human-computer interaction people, you have psychologists, you have even maybe philosophers and ethicists on the other side. So I'll hopefully just kind of break that down to you. So this will just be a quick, rough introduction as to what maybe people are doing, the kind of technologies they're doing, and then maybe some kind of future outlooks and what non-technical people, so people in governments and people, doctors specifically, what they maybe are looking for and what they want when they say explainable artificial intelligence versus what maybe an engineer might say when he says explainable AI. So this is just a quick overview of what we'll talk. So a good point, I guess, to start would be where did we get to this place? So there has been maybe 2 big reasons why AI has kind of infested every part of our lives. Why everybody's smartphone is kind of tracking him, has hundreds and hundreds of applications that will be using AI, whether that is when you're just Googling something, that Google has kept a track of maybe your previous searches, your location, what other people around you wanted, what's trending. So they can say more accurately what it is that you want or what they think that you want. If it'll be YouTube or TikTok or Instagram that they'll be recommending either videos or ads or both. Again, based on your prior usage and that. And then maybe even something more insidious, like if you're applying for a job, that there might be automatic filtering that goes whether or not you even get called for an interview or whether or not a human even looks at your application. And the reason it's become so prevalent like this is because it's so cheap to run models. For a very, very modest amount of money, you can rent GPUs from Google. I'm sure the university there has its own computer setups that maybe you can get time at, and it's become so cheap and readily accessible for everybody. And then the second bit would be vast amounts of data that were collected, maybe not knowing that they'd have this application, but just vast amounts of data that have been collected, have been stored cheaply, and now can be just fed into these algorithms and give really like impressive results. The reason why AI has been so successful is because it's so impressive, because these companies make so much more money. And like there is a phrase that you'd maybe hear, kind of a buzzword, that data is the new oil, which I think to an extent is still true. And maybe why you're seeing companies like Tesla have so much, be valued way more than say other car companies like Volkswagen or I don't know, Land Rover, Jaguar, these kind of things that have, if we were looking at say the actual car itself, the engine are probably comparable to Tesla. But what Tesla has way more than any of them is user data. So the Tesla actually is almost a computer software company more than it would be a car company. When you look at the amount of data they collect, how often they collect it, how they store it, and what they're planning on using for it. Which is why it's, I don't know, it's still the most valuable company in the world, or one of them anyway, and why Elon Musk is a billionaire, because it's data, not necessarily its technology. And again, this number, I think I got this number even from something last year. So this again could be even further and much higher than it already is now. So the motivation is clear. It's cheap to run these things. There's lots of data that's already been collected, is currently being collected, and it's cheap to store. And the potential, the companies you could make, and the potential value you could utilize from both of these things is just exponentially huge. And
Hello.
I'm back. Sorry about that.
Hello. Am I audible? Am I audible?
Can you hear me? Can you hear me?
Yes, we can.
Yeah, so could somebody just allow me to share my screen? I hope I wasn't talking to myself too much there.
Yes, you can share now. Yes, visible.
Yeah, okay. So when did I get kicked off? Was it around this slide?
it was in the motivation part. Yeah.
Yeah. Again, I suppose I don't need to labor the point too much. There's just lots of money available if you can create a company that is successful using AI in a smart way that can replace a human. But what is AI is a question that people don't even really agree upon a lot. So you have maybe people from 20, 30 years ago who would say, okay, we've got these expert systems, kind of decision trees, maybe basic statistical models with some kind of a knowledge base attached to it, humans creating these expert systems. That this would be their definition of AI. Whereas if you somebody maybe at Google or Facebook that are running these massive models that have billions of parameters, millions upon millions of inputs, take weeks and maybe months to train, millions in dollars in electricity. So these kind of two paradigms are so far away from each other to not even see any almost common overlap that you can maybe see in this diagram here on the right. So just, I guess, a basic thing maybe everyone could agree on would be at the very end. So if we can just define an AI, or maybe just even a model or an AI model, whatever you want, as just anything that would perform a job that a human normally would. So again, that might be classifying something. So if you go into a bank and you want to get a car loan, if they accept it or they reject it, if that is writing computer code, if that is driving a car, anything that a human would normally do, that a computer is doing, or we have some kind of mathematical model that's doing, we would call that AI just for the sake of this, which is a nice broad definition, and it allows us to actually kind of get into the interpretability without maybe worrying too much about what it is we're trying to interpret. And as well, for the sake of this, I'll just mention, but it's not too relevant for us, that if you look into the literature, there's maybe strong AI and weak AI. And so weak AI would be almost I would say actually everything we see in the world today. So where we have a task we collect some data on that task, we fit our model to it. So it's, again, we have some kind of classifier system, we have some maybe x-rays from the hospital, we have some weather data, we want to predict if it's going to rain or not. So we give it data, we have some algorithm that can take in this data, iteratively improves itself. It can maybe take in some expert knowledge, it can take in some new knowledge, maybe it does some kind of feature construction, something like that. But again, the idea is that this algorithm is set up to solve this problem. So we have data collected, we have features, we have human expertise, it solves this data. Strong AI, on the other hand, is this kind of futuristic, super intelligence that can learn by itself, is especially, not specialized at all, and essentially is a human, so that it can think. And the key to here is that weak AI kind of has the appearance that it can think. That, there's a phrase that all new technology appears like it's magic. So again, that when you show somebody an image recognition system on your phone, that you hold it up to a car, it recognizes it's a car. This isn't, it's kind of a simple example, but it appears like it's magic, whereas strong AI would actually be magic. And especially, it's kind of gotten a little bit of press. I don't know if this maybe got as far as India or not, but there was this Google engineer. This was maybe 2 months ago or a month ago. So Google were working on this chatbot, one of these new large language models, one of the numerous that have been released in the last kind of 6 months. And this guy, this engineer, I think he was a tester. I'm not exactly sure, but he wasn't necessarily like a head AI guy. He published an article saying that he thinks it might be sentient, that this chatbot was thinking for itself, it knew about its surroundings and all this kind of a thing, which is really, when you look into what that actually is kind of nonsense. So again, this chatbot is just trained on millions and millions of conversations, trained on millions of text data. There's nothing sentient about it. Just when you ask it, are you sentient? It will reply yes. It's not exactly super intelligent that's going to take over the world yet. So again, there is an awful lot of like spoof, we would call it in Ireland here. So again, people looking at something saying, wow, this is amazing, when actually they're just in their own brain applying amazingness to what is amazing engineering, what is in terms of like creating these things are very powerful, but are they human? Like, no, are they even safe to put out in the real world is questionable. And I think it is people just trying to find something that isn't really there yet. So this is the kind of black box models we're talking about. So these things that are the backbone of all of these AI companies that make them so much money. And these are usually in the big companies today, these would be kind of deep neural networks. There might be some support vector machines, or there might be some kind of more traditional machine learning, like nonlinear modeling, some clustering, k-means, that kind of stuff. And all we care about here is that we're inputting something into the model, it's outputting a prediction or a classification or something like that, and then we're using that as our pair. So with this set of data, we have this prediction, we run from that. We don't necessarily care what's going on in the middle. So we will run our tests and we will look at our accuracy to say, okay, well, I'm expecting this. It's giving me this 95% of the time, 90%, 96%. So that's good enough. Okay, we can put that into production, but it's, you know, it's not maybe necessarily ideal in all scenarios, and it can't be used in all scenarios when compared to something like a simple decision tree or a logistic regression, where you can look at exactly what features are going into our prediction, how exactly they're going to be weighted, and you know, there's like how it could be tricked, I guess, or where it would be bad. But these kind of deep neural nets will almost always be, I suppose, almost always have superior performance, which is why they're used and which is why they have all of the money and all of the funding behind them. But this does raise two concerns. So one is, as I was saying, the lack of insight. So if we're saying, okay, this is our data, this is our output, it's right 96% of the time, we don't know when that model is going to break the rules. Meaning, okay, we've given it some data to train on, it's doing its thing. We don't know if we give it another instance outside of that training, if it's doing something completely illegal or something completely wrong. That we don't know what it's you know, it's common sense, I call it here, but you know, that's what we as a human would call a common sense. That if we say, okay, we have a cat has 4 legs and whiskers and pointy ears, but if we come up with some kind of weird looking creature that has all of those features, we know it's not a cat. Or maybe a table that looks like a cat, well, we know it's a table. But of course, a machine doesn't have a concept of a table, let alone what's the difference between a cat table and a cat. So again, we don't know when this model will break the rules and potentially something catastrophic will happen. And then maybe even more so when we're looking at it in terms of, you know, computer scientists, if we want to be computer scientists as opposed to computer engineers, which there is differences, is that there's no new knowledge can be found. So if you want to be a scientist, it's maybe very anti-science to not even consider knowledge when we're running all of these things. So again, we want to maybe see any kind of breakthroughs that AI can help us. Maybe AI will be the first step in that knowledge, but at the minute, the AI is the first step is the only step that AI is taking. And then of course, trust. It can be very difficult to trust these things. Then obviously, if you're not sure when it will break the rules, you don't know if it has common sense, and you don't know if you can trust every single input output, that it will just catastrophically break and maybe cost money or jobs or something like that. And this is something that has happened continually over and over and over again. So in America, they had a system for testing whether or not somebody in prison who's coming out should get parole or not. So if they can be let out early with kind of certain conditions. And they were using a simple model for that it was found that it was maybe biased against African-American men when they were applying versus white men. So this is a pretty, this isn't a kind of a simple toy example. This is actual people's lives that has serious ramifications that is potentially showing bias. So saying Amazon has had these tools that have been shown to be sexist, particularly I think with hiring. If you kind of Google a lot of times, maybe image search might show you things that that again somehow are biasing or reinforcing any maybe bad stereotypes that might already exist in society. So this isn't necessarily the here. So this isn't necessarily the algorithm's fault or anything like that, because the algorithm is just as good as the data you will give it. So if you're giving it good data, it should hopefully, in theory, have a good output. If you're giving it bad data, it will have a bad output. But without any kind of insight into what's going on, or maybe kind of outlook, it's impossible to spot those kind of training data blind spots that maybe you didn't give it those images of cancer when it's in a certain region, that you didn't give it I don't know, when you're driving on the road, that you didn't give it when there's lots of horses or there's dogs on the side of the road, so it just drives straight over them. So again, these are all things that need that kind of maybe need interpretability to at least help you find, if not fix. And then even more so that I maybe talk to in just a little bit is the EU has had a big push towards this the last maybe 3 years. So aside from GDPR, which will look at how your data is stored for building these models, so it's just cookies on web browsers, or even your just personal data or images and stuff like that, or even they're going one further into complying exactly what kind of AI models you can build and how you can put them into the wild, so to speak, with really strict guidelines and fines, and pretty heavy fines if you're found to be breaking them. So yeah, so I guess the last point here is just the explanations then. When, okay, we've decided they're important, that we need them, they can just be kind of maybe broken down into two main areas. So how or why. So how was this decision made? So what were the factors that went into it? What was the weighting behind it? You know, if we change this, okay, would that change anything? So the kind of maybe the how, which would be maybe the engineering question to ask. Okay, how did I get to this decision? And then secondly would be the more why. So again, no, well, actually, why did I make this decision? Is there something we could change in our data set? Is this something that we want built in our system? Is this what we wanted to do? So again, the how or the why are kind of maybe two different sides of the explanation coin, that you have maybe engineers on one side, maybe ethicists or users, or maybe doctors or something on the other side. Okay, so when we go to the how and the why, even having trouble defining what AI is, we can even have trouble defining what model interpretability is. Because the how and the why will depend on the domain, will depend on the expert, and it will depend on the criticality of the system. So if you go into a bank to approve a car loan, you just need to show the how is it just didn't discriminate against you. So if it didn't say, oh, well, you are a woman, so that's why we didn't give you a loan. If you were a man, we would have given you this loan. If you are whatever, say you're disabled or something like that. So again, all we need to show there, the how and the why of this model interpretability is just simply, oh, we didn't break any law. Because again, if this is maybe non-optimal, it's, you know, there's no lives at stake here. We just need to simply show, well, we're not breaking any anti-discrimination laws. You're getting your car loan, you're not getting a car loan. If you bought that car and it has a self-driving in it, then the how and the why are much, much more different. The how and the why here, every step is critical. And there's, again, if you were to go onto Google Scholar and search for this, there's hundreds and hundreds of examples of showing like really, really easily how these self-driving systems can be tricked. That how it recognizes a stop sign. It doesn't need to there's no easy how or why of that. It needs to explicitly recognize a stop sign. It needs to recognize the S, the T, the O, the P. It needs to recognize them in that order, and it needs to recognize once that is made, it means stop. It means that if we have a malformed S, say the paint has scraped away, say there's some stickers on the stop sign, say there's some graffiti, that self-car still needs to know the how and the why. So again, knowing how it recognizes a stop sign, how it recognizes somebody walking in front, how it recognizes a motorcycle, how it recognizes anything. Every step is critical. So the how and the why there is again different. So when we said, okay, we don't exactly know what AI is, we're saying, okay, it's any model that does something a human can do. What is model interpretability? Again, it needs to be centered on both. It's the how and the why that the problem needs. So this can be broken down in this kind of picture here that I've scraped from the internet. So if we follow here to the right, we have an explainable method that we want to look at the scope. So it can be either global or local. So global in scope means that we are looking at the entire model, what it's doing as its logic. So a very simple example could be, say, if we somebody came into a hospital and we needed to decide if they go see a doctor straight away or they have to wait until the queue. So they could say, okay, if your temperature is above a certain if your temperature is above a certain threshold, that you skip the queue, otherwise you have to wait. So that is a global explanation of the logic of the model. So anyone can read that and know exactly what's going to happen 100% of the time, always. That the logic is rock solid, and this is how it's applied across every case. A local example then would almost be the opposite. So say somebody had skipped the queue, and you wanted to query, okay, your model, why was this person admitted? Then they would say, oh, well, their temperature was above their temperature was this, and it's above the threshold, therefore they skipped the queue. So a global will give you everything, a local will give you a case-by-case basis, and then from those cases you have to almost try infer the logic. So again, we can see global is a lot more rock solid and impossible to get on most cases, because again, if you're trying to understand the logic, we had a simple one rule system there. If you're trying to even include 5, 6, 7 rules, trying to understand the logic would be almost impossible. And again, maybe it's something you don't necessarily need. You don't necessarily need always maybe a local explanation, that on a case-by-case basis as they come up, you just simply need to check that, no, this logic makes sense why they skipped the queue. And then at the bottom, it's two things I'm not a huge fan of. So we have maybe intrinsic model specification. So that's saying, okay, well, no, this model is explainable. So we've got a decision tree. And then to the right, we have a post hoc, which is saying we have this model explain my decisions. So again, like say we have this big neural network. Somebody gets skipped the queue in a hospital, and they say, oh, well, why did they skip the queue? You can query that black box, and it will give you, like I was saying, a local explanation. Oh, well, its temperature is high, and this is above a certain threshold. So explaining. So I'll just quickly run through maybe the techniques people use now before I go on to maybe criticize why having maybe an intrinsic specification can be difficult, and why this post hoc is a lot more difficult than it sounds. So there's 3 ways then of opening a black box. Generally, there's a lot more than 3, and again, because this is kind of at the top of its popularity at the minute, and there's so much money, there's more and more coming out every day. But essentially, you can break them down into 1. Take your black box and try and create an intrinsically interpretable proxy. So start with my black box. can we somehow turn it into a decision tree? The second will be feature importance. So again, just showing you, okay, these are the 3 things that are mainly responsible for our decision. Are they okay? They're not breaking any rules. Logically, it makes sense that these are the things you would consider. And then finally, and this is mostly just for images, is visualization. So can you put a mask over an image that will maybe show you the important parts of the image the neural network is focusing on? And that will, you can infer the logic then. Because again, if you're looking at a stop sign, or if you're driving, is the car looking at the stop sign? It's looking at the shape of the sign. It's looking at the writing on it. It's not looking at where the pole is in relation to the side of the road. It's not looking at the sky. It's not looking at the street. That this is all it's, you know, when it sees a stop sign, it knows to stop. So creating an intrinsically in proxy, what you will do is you will fit your model, you have your input, your output, from your input-output pairs. So not necessarily your data input-output, but your input-output from the black box. You will take those pairs and you will fit your decision tree. So again, if we can say, okay, we fit a really good decision tree, linear model, logistic regression, whatever it is, to not what our input-output is, but what the black box input-output is, then we can infer from that that this is the logic of the black box. So again, it's in theory quite nice. And there is lots of people that would do this for maybe sense checking as opposed to anything more than that. Because again, if you have a good decision tree that will approximate really well what your black box is doing, you would just fit that decision tree to the original data to begin with. So again, when you say, okay, we have a black box that's approximating the data, maybe 95%, and then we build a decision tree that approximates the black box input-output at maybe 70%, it's not exactly, again, we don't know when it's going to fail. We couldn't say if we wanted to trick the black box, we wouldn't maybe necessarily know from that decision tree what our you know, what our adversarial output should, or what our adversarial input should look like. And as well, we are, you know, we're not maybe gaining anything from this, only wasting more computational time for something that maybe we'll just try convince ourselves that this model is okay because this decision tree is okay. But the plus side of this is that you don't need too much understanding of computer science, that if you give somebody a decision tree, even if they're, and even a non-expert in the issue, they'll be able to understand what's going on. So that is why it is attractive. But again, it's not exactly, it's not really feasible for a lot of things. It's not preferable for a lot of things. What is used most, and if you talk to people in industry, if they're doing kind of XAI stuff, it will be feature importance or feature ranking. So again, I think this is from Lime, yeah. So this Lime here, this local agnostic model explanations, or whatever it is one of the most popular, or else maybe kind of SHAP, which I'll just explain in a bit. But what you essentially do again is you will build your model. You will then perturb your input outputs, then watch how that changes you'll perturb your inputs and watch how that changes the output. So if I have an input, it gives me an output. If I change feature 1, if I change feature 2, change feature 3, how much I change them, how does it change my output? From that, then you can infer how important a certain input was to the output. So again, we can see here that if we have from our data that there is no fatigue, so we can change fatigue from yes to no, and it doesn't change our output. So therefore, we can say this had absolutely no importance in how we made our decision. We can change our headache. So we change from headache from yes to no. Oh, well, our decision changed. So okay, well, so obviously headache is a part of our decision, and this is an important thing. An important thing our model considered. So again, you can give that to a human. A human can sense check that, saying, okay, well, it makes sense that this is considered. This is considered. Yeah, okay, well, this all kind of makes sense. And that can kind of give you, okay, not necessarily the logic of what exactly is going on, not exactly how sneezing and headache interact with no fatigue, how that happens, but it can tell you that the model is looking at the right areas and considering the right things I would want it to consider. So again, these Lime and CHAP. So if you go on to Google Scholar, these things have thousands and thousands of citations in only a few years. So like this Lime thing came out just as I started doing my PhD, kind of 2017, 2018, and really, really popular, and is used not only in say toy examples that you could play around with on your own stuff, but also at the very top companies, and like all of these companies would be using these types of things because they are the best. However, it does come with maybe the cost of having to perturb your data, and again, we're not sure necessarily when this will break down, because it will tell you what features are important, but it won't necessarily tell you what's the limit they can be pushed to necessarily. And again, as you become more complicated, the logic might fall down a little bit. And as I'll show later, actually showing these to experts isn't necessarily good for sense checking. It might actually just confirm whatever biases or blind spots they have. And then finally, visualization, which I think is really clear. It will just show you where the neural net is looking and the important pixels in each image. So again, here we can see this third image here, that it's asking what color is this fire hydrant here, red, that we have on this third image here, that it's looking at something completely random off to the side. Again, this is obviously really useful, and for sense checking especially is, you almost don't need an expert, because you can just look, where is it looking? Is this the feature that we wanted to look at? We can compare it to human attention and see how it's doing. But however, this won't necessarily tell you how to correct it, because again, we can see here on this sand too, okay, well, it's mostly looking at our fire hydrant. Okay, there's something off to the side here. It's looking at maybe a tree or a I don't know, or maybe is that a pole, something like that. So we don't know exactly how we could improve this. We just know something is going wrong with our model. Okay, how do we debug this? Do we go to certain neurons that we need to deactivate? Do we need to give it more training images? Do we need to just crop that bit out of the image and then maybe refit it? Does that fix our problem? So while these are definitely good as sense checks, we need them when we're doing anything that will be safety critical. But okay, actually, how useful is this to debug? Is this quite difficult? And yeah, as I was saying, and ambiguity, especially with visualization, can be tough, because again, say there's only 2 or 3 pixels looking to the side. Is that okay? What if it's 5? What if it's 10? What if it's 50-50? What if it's picking up the main bit and that we want? Maybe there is something associated with a red fire hydrant that humans wouldn't consider, but maybe a computer would. So maybe it isn't that big of a deal. But again, this kind of ambiguity is quite difficult. So the main issue I would have with saying that a model is intrinsically interpretable and a model is intrinsically uninterpretable is that you just really can't say that. Because, okay, if we have a decision tree that is depth 2, or even the example I said that, well, if you have a high temperature, you skip the queue. If you don't, you have to wait in the queue. That's fine. But what if we had 30 variables all interacting with each other non-linearly? Or what if that had different what if your temperature had different variable cutoffs depending on your weight or your gender or your age or something like that? So to say anything is intrinsically interpretable is a big problem in my opinion. So I'll just quickly show you some stuff I've done. So I was creating these trees that kind of combined fuzzy logic and linear regression type thing. So again, it's just so this is a computer tree that you don't necessarily need to know what, max heart rate and these kind of things. So this is just looking for heart disease. So I gave these trees to an expert and they scored them from 5 to 1. So here we have something that they scored as a 5, that they could look at the different variables, how they interact, and they could understand exactly, okay, what's going on here. okay, well, I know if you give me this input, I could tell you what the score would be. If you give me that, oh, I know exactly maybe where it would fall, or if I wanted to trick it, here's an example I could give. So this is the exact same structure, but with an interpretability score of a 1. So again, I gave this to the expert, and the expert said, I don't have a clue what's going on here. We have loads of variables interacting nonlinearly. We have loads of these operators, these kind of weighted average, these maxes, these mins that are going max, min, max, min, max. So again, if I was to go and say, okay, these fuzzy pattern trees, as they're called, these trees that I'm creating, they're an intrinsically interpretable model. Well, not really. I mean, they're intrinsically interpretable if they're maybe small, if they don't have lots of variables, they don't have lots of interactions, they don't have lots of complicated interactions. So to say that a model is intrinsically interpretable, I think is a problem, that it's just context related, and that it's only if it's maybe within a certain difficulty score. So again, I think intrinsically interpretable is maybe a bad way to go about things. And even maybe more recently, the push for this interpretability has taken a step back with what the EU has set out. So the EU has set, and the European Commission has set out to regulate what AI is, and as it is here, is that it should be as neutral as possible. So again, we're saying neutral as possible. Okay, this is good. So we say, we've shown that, okay, all these XAI techniques that we've shown, that they will allow us to kind of hit this neutrality, that we can say, okay, it's not biasing against any gender or age or race or anything like that, that we can say it's safe to put in because we've shown that it's logic, we've looked at it, that it's kind of rock solid, we're happy with it, and that this is good. It's as neutral as possible, it's not offending anything. But yeah, and then this is just more, not necessarily with the explainable part, but just what is permitted. So again, any kind of safety critical, any kind of thing that will affect your population drastically requires different levels of this neutrality. So again, we're seeing here that if we have this unacceptable risk, so social scoring, which is just prohibited, but you have things maybe in medical devices, in recruitment, in access to credit, stuff like that, that we have to have compliance with AI requirements and conformity assessments. And then it's slightly lower down, we need to be subject to transparency applications. So you think, okay, this is good, this is all setting up nicely, that we can build some kind of maybe XAI framework that the EU, so a government, will give us, which I think engineers actually would prefer, that, okay, no, these are the rules of the game, build me something within this. But actually, there is no requirement for explainability in any of their guidelines. So this is, I think, maybe early next year, this might be coming into law. So lots of the AI that's already in the market will be illegal, and lots of it will be needed to be retested. But what the EU want is that they want transparency in the system and extensive testing and feature logging, debugging, and auditing. So they have kind of come to the maybe same conclusion that that I've kind of seen, and I've maybe come around to here, that actually explainability is it's almost too much to ask for anything that is not supercritical, and on those supercritical systems where you have human oversight anywhere. So again, if you're giving things to doctors, if you're giving self-driving cars, things like that, that within that testing these things is actually far more important than trying to understand the logic or getting a human to sign off on them, because actually that they've shown that humans, this paper here, which from Microsoft, that they actually have shown that humans are far more likely to introduce bias into these things than a well-tested software would be. So it's a really interesting paper that people, I think, should look at if you're interested in this. that they essentially said here, that I've kind of highlighted in bold there, that if you gave these, I think they were doctors, but it's been a while since I read this, I could be wrong. If you gave a model that was clear, that had some bias in it, gave it to a user, an expert, or whatever you want to, whatever it was, that they were less able to detect, or they were even able to say, okay, there's some bias here, but I'm okay. They were less able to detect and kind of take those models out than if you just had a really rigorous testing setup. That you had your engineers, you had them write unit tests, you had them come up with adversarial examples, you had them come up with corner cases that you wanted, definitely. Any model that fails these can't be used. Okay, you need to refit, you need to build your model around these cases. That they were far better than actually giving it to a human to try find these things. And again, when you look, there is far more and more of this coming up. So when you look at actually the kind of things that Google are doing around breast cancer, that lots of them aren't in hospitals anymore. There was a report from the NHS in the UK saying that the stuff that AI, those tools are doing, are so far away from being usable in hospitals because of this kind of a thing here. That these hospitals, and I suppose maybe the insurance companies in maybe America, or stakeholders in general, are saying, right, no, you need to prove without a shadow of a doubt that these are safe to be used. That okay, maybe they can augment a human, that they can detect something that a human can't, these kind of things. But we're seeing more and more that these systems that I'm back. Yeah, so I was pretty much at the end of the talk anyway, but essentially just saying that we have, okay, these things, that these models that people are almost unable to bias, even when we give them the interpretability, and we're not getting to the nature of these systems. So that interpretability, I think, needs to just take a slight turn towards a more maybe scientific understanding of, okay, what is the problem, as opposed to explaining what it already has and then hoping a human can pick it up. But yeah, I'm happy to answer any questions if anyone has any. And I'll get my presentation back up. So we're back to it.
Thank you, sir.
I think I have to stop sharing if I want to see the chat, do I?
Hello. Thank you, sir.
Thanks. Yeah.
Now the session is open for the discussion. If anyone is having any question, you may please ask. I think, sir, there is no question from the audience.
Hi, excuse me. Can I ask a question?
Yes. You may please ask.
Yeah. Hi, Eden. Thanks for the interesting presentation. Really learned a lot today. So I actually have one question no, it's not exactly from model perspective, but let's say instead of focusing more on what the model brings into, do you think the data what we are giving to the model makes more it has more role as compared to what the model brings into? For example, if the data itself has a lot of biases, then of course the model is going to learn what the data has been provided. So what do you think about this?
Hi, Gary. Yeah, no, it's definitely true. So there's maybe two ways you could think about this. So that example I showed of the people coming out of prison to decide if they get parole or not.
Yeah.
Okay, so you can say that this model is biased, or you could say, okay, no, this is actually reflective of what's this is a bigger issue in society.
Yeah.
So you could say, okay, we need to correct our data to give us the output that we would want in an ideal society, and maybe kind of ignore the reality of what the data is telling us.
Oh.
Would be one side. Or the other side, it would be, yeah, you have, say, toxic data. And again, there's so much in the last kind of 2 or 3 years. There's been so much reported on these data sets that kind of Google and all these people are using are so huge that they're almost impossible to be curated. That you've got millions and millions and millions of inputs of images or text data, stuff like that.
Right.
That they can't be curated.
Yeah,
So
I
I guess to go to your point though, yeah, if you wanted to build a model using maybe some real world data that's maybe been corrected, or some hard coded examples that you want to give to build your model, I think that's fine. But again, you would need to trust that you would need some kind of technique to ensure that we're giving it the right data, but it's also using that right data in the right way.
Yeah, makes sense. Yeah.
Yeah.
Thank you, Eden. Yeah.
No problem, Gary. Thanks.
Hello, sir. I have a question.
Yeah, please.
So the black box, can we actually read it, or is it just not possible to read inside the process? We have the input and the output. So can we read the process?
No, like directly you can't, no, because again, it's just, say if you're going to do a neural net, you'll just have layers upon layers and just numbers and stuff feeding into that, so you can't possibly follow the logic.
Sir.
Hello.
Yeah. Am I audible?
Yeah, I can hear you. Yeah, go ahead.
So there is question. Hello, Adam sir.
Yes.
Am I audible to you?
Yeah, I can hear you.
Can we humans, can we understand what's happening inside the black box?
No, not directly, no. So that's why you need these methods to either, okay, make a decision tree to maybe explain what's going on, do visualizations, but actually looking at what is going on. Yeah. No, because if you look at even the architecture of a neural network, it's just impossible to try follow what's going on.
Thank you, sir.
No, thank you.
Is there any other question?
Yeah, okay, so I think that's the time of, yeah, if anyone wants to contact me, I think my email is at the and if not yet, you could find me on, say, LinkedIn or something, or Magna would have my email, or I'm sure other people have my email if anyone wants to contact me.
Thank you, sir, for enlightening us on the emergent area, explainable AI, which is actually a new branch of ML. In this session, so initially focused on a difference between the strong and weak AI, and then the need of explainable AI. So then explain explainability method with examples, and then how to create intrinsically interpretable model proxy, and with the various problems with the current approaches. And then he explained very well explainable AI. So thank you, sir. Thank you very much. So
Yeah,
with
thank
this,
you.
I here conclude that, and I declare that this session is over. Thank you, sir.
Have a good afternoon, everyone. Thank you.